All right, in this video, we've already learned how to graph polynomials, so I'm just going to show you how you can take advantage of your TI Inspire to help you with some of the application problems. Because sometimes our polynomials can look very large, like the one up at the top here, providing the precipitation of Picardville, I know, very inventive, for each month of the year. January will be month number 1, and then you work your way up to month number 12. So we're doing a domain of literally just t between 1 and 12, because it wouldn't make much sense to go much outside of the first month or the 12th month of the year, since there aren't months after that. But after this, again, the formula just repeats year after year. This is what we basically found to be the average monthly rainfall in Picardville. Now, what we want to do is instead, step number 2, determine the month with the greatest and the month with the least precipitation. We can see on the graph that it looks to be over here is the greatest, but again, that's pretty hard to find. And also, if we look carefully, it appears that down here is probably our minimum, especially since, again, this part of the graph doesn't really matter. So that's our lowest point. So what we can do is, if we plot that on our calculators, so I got that here, again, just go to Menu, Analyze, and we can find the minimums and the maximums. Remember, it's only going to find the minimum over a certain area. So if my minimum is right around where the hand is right now, I'm going to go a little bit to the left and click. And when I scroll to the right, it's going to provide me the lowest point between my two lines right now as I move to the right. When I pass that minimum, that becomes the lowest point on my graph permanently. So 4.426 approximately appears to be my x-coordinate here, 4.426. Well, we know that month number 4 is April, and that's obviously during April, so I would say the minimum or the least, right, amount of rainfall happens in April. Now let's go find the maximum or the most rainfall that will happen. So again, we think it's somewhere over in this area. We can go to our calculators, Menu, Analyze, Maximum, and again, click twice, and we should find out that at 9.779, so at about 9.779, or during the month of September, we get the maximum rainfall. Now, if they had actually asked us for the amount of rainfall that was the least or the greatest, right, then we could have actually provided the y value to go with it, which on our graph, again, is provided right here in our 2 coordinates. But they just asked for the x, or the month in which it happened, so we didn't need to do that. Another application can be making a box, and often you'll see in math books them asking you to make a box out of a piece of cardboard by cutting out the corners, okay, of this box. So to draw the situation, I'm just going to show that I'm going to cut the corners out of my box right here, right? And then once those corners are gone, we've kind of got flaps here made outside of these dotted lines. And you can fold up those flaps. And again, this flap here, right, would be the front of the box. And then we can make those other flaps kind of go together, right, forming a box as we fold them up. So this side, again, is basically right here in my picture. Now, what we want to do is determine a formula for the volume of the box. So if we know that this sheet of cardboard was 18 total units when we started, and we cut out x units, right, on each side for these corners, then the sides of my box are 18 minus 2 x's on this side, 18 minus another 2 x's on this side, and of course these two parts that come together, right, when the flaps are folded up, form this edge of the box, and they are just x units wide. So the volume of the box will be equal to x times 18 minus 2x squared. You can FOIL that out if you want to, but it's not necessary. That looks like a pretty good formula for the volume of the box. The domain of our box is saying what possible x's can we use to make this box. Remember, we're limited on the size due to the size of the cardboard. So what's the smallest x, right, that we could cut out of the corners and still form a box? Well, if we cut it just a tiny amount out of those corners, we can get really, really, really close to 0. If you're telling me that 1 is the lowest you can go, don't forget there's fractions and decimals. I could cut a half an inch, I could cut a quarter of an inch, I could cut tiny, tiny amounts. But I would say we can't cut below 0. I would also say you can't cut exactly 0 because that's just the bottom of a box. But you could argue that either way. If you want to make that or equal to, I wouldn't argue with you. Now what's the largest? Again, along those same lines, what's the biggest thing I could cut out of the corner of my box? Some might say 18, because again, that's the length of the side of the box, but remember that you're cutting 2 parts out of there. And so if this one gets a little bit bigger and this one gets a little bit bigger, somewhere in the middle we're going to meet for the largest possible spot to cut out. Or if we think about it, we just need to make sure that this side of our box, this part, right, our length and our width, don't go below 0. So when would 18 minus 2x equal 0 or stay greater than 0? Well, if we add 2x to the other side and divide by 2, we'll find out that x just needs to stay less than, right? 9 is greater than x, so x needs to stay less than 9 units. What that helps us with is next I want to find the volume of the box, and in order to do that, I'm going to need to graph it. But if I hop on my calculator, I open up a new document here, and we go to graph. So I'm going to type x and 18 minus 2x quantity squared, so squared, and I graph that. Oops, and I forgot that your calculator likes to have a multiplication symbol in there if it ever gives you that error. It's really hard to see much because, again, I haven't really narrowed in my real-world domain. So remember, we determined a domain of from 0 up to, at most, 9 units. And notice how my graph is now right at the edges of my screen. I don't know how high up to make this thing go, but if I name the domain to start, your calculator has a great setting under Window called Zoom Fit. It's going to leave the domain alone. It's going to leave me from 0 to 9, but it will find me y values that exist nicely in between there. And remember, if I went outside of that, let's say we kept this thing going, and I went over to -2, your graph starts shooting back upwards here. So if they talk about maximums, that's infinitely going up. Wouldn't the maximum be infinity? But remember, I can't cut negative amounts out of the corners of the box, so this side of the graph makes no sense. We only want to look from 0 to 9 because only these points are actual boxes we could make. And therefore, where's the maximum? Well, it's going to be right above my function there if I can move that out of the way. So let's find that maximum. Menu, Analyze, Maximum, click and click, and it looks like at 4.5, 16.4025. So let's hop on here and we'll say, we'll determine what x value provides the maximum volume. From the looks of our graph, that was at 4.5. And what is the maximum volume? Now that's the output, right? Volume was our function. So when we figured that out, I'm just going to take us a quick picture here for all the stuff we needed. Once we figured out that part, we know that 1,640.25, and we are dealing in inches, so inches cubed would be our maximum volume. Again, 4.5 inches is what we're going to cut out of the edges of the box. I hope that helps you as far as applications of graphing, why we would use those maximums and minimums, how they would be, helpful in the real world. Good luck and have fun.